They've been separated like for 64 million years, that alligator line and the crocodile line. So they're physiologically, they're quite different. And look, no one's quite sure which came first really, whether these things, saltwater crocodiles, whether that line evolved from a marine ancestor, because some of the crocs used to be like dolphins and, you know, there was such a diversity. And so there's some evidence to suggest these crocs did evolve from a marine ancestry and they kept the salt glands. The alligators, that whole group of crocs, alligators and caimans, they don't have the salt glands, whereas all the crocs have it even if they don't live in salt water. The glands in the tongue, the salt glands, actually pump out the salt. So when they take in salt water, the glands pump it out so that they keep a homeostasis. But saltwater crocodiles really do best, I think, in freshwater. Now the heart, what makes crocs different is that the pulmonary artery, right, that's going to the lungs, comes out of the right ventricle. The systemic artery going to the body comes out of the left ventricle. That's all clear. In mammals, that vessel going out is the embryonic left systemic artery, whereas in crocodiles, it's the right systemic, and they still have the left systemic, but the left systemic opens from the other side. The vessel that takes the oxygenated blood out to the body in most animals that's it. In crocodiles, there is another vessel that actually opens from the other side of the heart. It's a smaller vessel, but it goes out to the other parts of the body. So it's actually taking deoxygenated blood back to the body instead of sending it to the lungs. You can see those little nodules there. They had never been described before. And that's the pulmonary artery. So when it starts to pump, those nodules close that off, the pressure keeps building up, and then bang, these valves open here, and the deoxygenated blood with no oxygen gets pumped back around to the body. On the other side, you've got the normal right vessel, that's the main aorta going out. So this is really a most weird situation, that the left and the right come out together like this, but the valves underneath there's a hole through there. So when the heart stops pumping like this, the blood from this side can go there or this side can go there through the left and right systemics. Called the foramen of Panitz. So although it's a four-chambered heart, it really has been an enigma how all these strange things happened. Now that left systemic actually goes around, the one that comes out from the lung side, goes around and supplies mainly the stomach and the intestines. It goes backwards. And when you question how the architecture of the heart could come up with this, the only thing I could ever think was that at some time in the past that they possibly used the tail for respiration in an aquatic environment. Like they used it, were able to perfuse blood through it and get oxygen or something. So that in some of the ancestors of these things, it was important to have the option of sending some of that blood around to the back of the animal rather than keep it all inside. That would make sense as to why the left systemic would be there, because you could shut off the lungs if you were diving and still oxygenate the blood by pumping blood around to the exterior of the animal. Something like that's created the sort of major change that was necessary to put the left systemic over on the pulmonary side.